So let us repeat the idea. Okay, we were talking about different behaviors of fluids. So for shear thinning, what will happen is that the viscosity will decrease with the shear rate. So here you can see this figure. The slope is decreasing with higher shear rate. So this means that the harder the fluid is sheared, the less viscous it will become. Okay. One of the most common examples of this behavior is latex paint. Okay, because if you consider latex paint, it does not drip from the brush because the shear rate is small. And the viscosity is large. However, when you put the brush on the wall, the paint will flow smoothly onto the wall because of the thin layer of paint between the wall and the brush that will cause a large shear rate and a small viscosity. Okay, so latex paint is one of the common examples for shear thinning fluids. On the other hand, the example your friend gave for mixture of sand and water, this is the case of shear thickening, because for a shear thickening fluid, what will happen is more you mix, more you increase the shear rate, higher will be the viscosity. Okay, so these are different behaviors of fluids. Now, uh, another important characteristics of materials is the viscoelastic behavior. So until now, we have seen what is the elastic.
Doctor,
Yes,
could you go back to the previous slide, please?
yes,
في non-Newtonian plastics.
yes.
Could you give an
Non-Newtonian
example?
plastic is characterized by a very high increase in viscosity with shear rate. So as you can see here, the viscosity the viscosity decreases in a very high rate with shear rate. This is called the Newtonian plastic. Okay, so you can reach nearly zero viscosity for a certain shear rate. Okay, this is called the non-Newtonian plastic. Okay, so as you can
Yes, okay,
see,
thank
you
you.
have a dramatic decrease of viscosity with shear rate until nearly reaching a zero viscosity stage, nearly, which will be close to the behavior of an inviscid fluid. An inviscid fluid has a viscosity that is close to zero. Inviscid it means zero. In real life, we don't have purely inviscid fluids, but the closer you are to zero viscosity, you will be closer to the inviscid fluid. Okay.
Yes, thank you.
What is the sign إنه ال viscosity is decreasing
The sign
بالجراف؟
of viscosity is decreasing. يعني if you are doing if you have a fluid and try to mix it, it will be difficult to mix it if you have high viscosity, while it will be easy to mix it if it has a low viscosity, because viscosity is the opposition to relative fluid motion. Okay.
Okay, and the graph إنه شو اللي بيخلينا نعرف إنه ال viscosity is decreasing؟
The slope, because what is the relation between shear stress and shear rate? Shear stress is viscosity times shear rate. Okay, so the slope at any point, at any location, okay, the slope of the graph represents the viscosity. Okay, so here for a Newtonian fluid, you have a linear variation, so you have a constant slope. For example, shear thinning, what is happening, the slope is decreasing, so you have the reduced viscosity. Okay.
Okay.
So now we will go back to the viscoelastic behavior. Okay. Now, until now, we have discussed what is the elastic behavior. Now, what about the viscoelastic behavior? It's a material property that determines the strain that the material will experience when subjected to combinations of stress and temperature variation over time. So this is combination of viscosity and elasticity property. Let us see a graph that will illustrate for us the viscoelastic behavior. It's not that are directly proportional. The slope is the viscosity, Karim. Okay, the slope of the graph is the viscosity, because you are multiplying, by definition, you have that the shear is you have the tau, okay? You have tau is, yes, if you want, tau is equal to the shear rate times the viscosity, okay? In general, the slope is defined as d tau by d gamma, okay? So if you want, at each instant, if you want, it's like an instantaneous slope. Yes, if you want, it's just the slope for the Newtonian case, and for the Newtonian case, it's directly equal. The slope is directly equal to the viscosity. For the other fluids where you have variation of viscosity, you have a certain proportionality between the viscosity and the slope. Okay. Okay. So let us continue. Now, in this graph, okay, you have the elastic behavior versus the viscoelastic behavior. We will see how a material will respond to variation of stress. In case of elastic materials, the response will be spontaneous. So here, if I put instantaneous stress, then I will have instantaneous increase in strain. And once I stop to increase the stress, I maintain the stress constant, my material will maintain a constant strain. It will not deform anymore. And when I move my stress, it will instantaneously go back to the initial state. This is the elastic behavior. On the other hand, for the viscoelastic behavior, I have the following case. I have that when I put a certain stress first, the strain will increase, okay? But if I maintain the stress constant, I will have gradual increase of the strain with time. So the response of strain to stress is not instantaneous in case of viscoelastic behavior. And then if I remove my stress, also I will not have instantaneous, if you want, I will not go back instantaneously to the initial state. I will go to the initial state, but after a certain period of time, so following a certain curve. So this is what is called the viscoelastic behavior. It will not respond instantaneously to stress. So this is in summary all of the information required in chapter 3. We are done with chapter 3, and I prepare a formula sheet for you, which is summarizing all formulas in this chapter and in the chapters that will be included in the exam. So this is the formula sheet. In this formula sheet, you have all equations that you will use in problems. So here you have the engineering stress, the engineering strain, the ductility measurement, the tensile strength, the true stress and true strain, the elastic relationship. Now, for the strain hardening region flow curve, you have sigma equal k epsilon n. And also, we will demonstrate together in problems that we can relate the engineering stress and strain to the true stress and strain. And this relation is given by the following equations. I want you to think about how to demonstrate these equations, and I will set for you several problems to try to do. Okay. Of course, there is exercises for the chapter. I will post them soon for you. During the weekend, you can start to do them as a practice. And I will give you time to practice with them. And so next week, we finish the material for the exam to give you time to study. And after, we start doing problems on all chapters. And we will do problems on chapter 3, and we'll do some problems on other chapters. But mainly chapter 3 is the biggest chapter among the other ones. Okay. So try to derive these relations between true stress and engineering stress and strain. And for the Brinell hardness, I told you I will give you a formula. If you remember, we have introduced Brinell hardness last time. So it is here. It's a way to measure hardness. It consists on applying a certain force on a ball. Okay. And under the effect of this force, what will happen is that it will cause a permanent indentation in the material. So we can express the Brinell hardness as function of the applied force, the diameter of the ball, and the indentation diameter. So here, this is the formula which will give you the Brinell hardness, but just please pay attention for the units. So if you don't put the units, you will get wrong results. So here F don't, you think that F is a force, it should be in Newton. No, here we use F in kilogram, and it represents the mass of the ball that you press on the specimen. Okay, so please pay attention for this. Don't convert to Newton, it's F in kilogram. So if I give you the weight in Newton, you should transform it to kilogram to replace in the equation. And the diameter of the ball and the indentation diameter are in millimeter. So to obtain accurate results, you should pay attention for units. Okay. Now, in general, when we did these tests on Brinell hardness, the majority of tested materials were metals, and one of the most tested one was steel. This is why we come up with a certain empirical relation between the tensile strength and the Brinell hardness. So if you measure the Brinell hardness of a steel, you can deduce its tensile strength through this empirical relation, and the tensile strength will be in megapascal. Okay. Now, concerning the other formulas of this chapter, you have the relation between empirical relation between shear modulus and modulus of elasticity that we have seen together. You have empirical relation between shear strength and tensile strength also. So if you know properties of a from a shear test, you can deduce properties of tensile test. And finally, you have the definition of shear viscosity. Okay. Now, what you should know also, but not in this chapter, you still have little formulas that will be covered in future chapters. But as you can see, the majority of formulas are covered in chapter 6. Okay. So as I told you, I will post an assignment for you to try to do problems. And meanwhile, next week we will finish the material of the exam, chapters 6 and 7. Okay. And in this way, you will have enough time to study. And in the remaining time, we do review problems together. So now I will start a new chapter with you, which is chapter 6. It's an easy chapter. And mainly it is, if you want, it is more experimental. This is why for this chapter, I prepared for you several YouTube links that will, so you can see in real, you can see live how we do measurements, what are the equipment used in measurements in manufacturing, etc. Okay, so in this chapter we will tackle dimensions, tolerances, and surfaces. So you know that dimensions are very important, and in any project in any final object you want to you should do you should draw first what is your desired product. You should put dimensions on it to be able to manufacture it. And you know that in any manufacturing processes you might have some errors. Okay, so this is called the tolerances. In any process, they will tell you this process can give you tolerances plus or minus, for example, 0.1 millimeter. Okay, so it's very important to know. It depends on your the accuracy you need. If you need a very high accuracy, you should go with more advanced manufacturing processes to obtain the desired object. And in this chapter, we will go also over conventional measuring instruments and gauges, and we will see properties of surfaces. So to start with, we'll define what is dimensions and tolerance. So of course, you know what is dimension. It's a factor that determines the performance of a manufactured product other than mechanical and physical properties. And it includes dimensions as linear or angular sizes of a component, and tolerances, which are the allowable variations from the specified dimensions that are permitted in manufacturing. So in general, the dimension is, if you want, is a subjective scale, because you can now create a new scale and say you just say, for example, I want to come up with a new unit. Let's say 1 unit of my scale is equal to 1.2 meter, for example, and then you define a scale. So a dimension is a numerical value expressed in appropriate units of measure and indicated on a drawing and in other documents along with lines, symbols, and notes to define the size or geometric characteristic or both of a part or a part feature. So, for example, when we defined the meter, okay, we come up with a certain length, and we said this will be 1 meter, and this is our reference. Okay, all other lengths can be expressed function of meter. Okay, and you have several scales. You have the SI scale in meter. You have the English scale in feet. Okay, so you have several scales. Always you have a reference dimension, and based on this dimension, you can define any length. And the dimension will indicate the part size desired by the designer. If the part could be made with no errors, but in real life, you always have errors. This is why any manufacturing process should tell you what is the tolerance of this process to know if it's suitable for you or not. Okay? And the definition of a tolerance is the total amount by which a specific dimension is permitted to vary. The tolerance is the difference between the maximum and the minimum limits. And in general, we have variation in any manufacturing process, but we have manufacturing processes that are more accurate than others. Okay. Now, tolerances are used to define the limits of the allowed variation. For example, here, one type of tolerance is bilateral tolerance. In this case, you allow for variation in from both sides in the positive and negative directions. This means, for example, if you want to produce a shaft and the diameter of the shaft should be 2.5 centimeter, for example, you say that I can have maximum a diameter of 2.505. Okay, or I can have minimum 2.495. Okay, so if you specify your limits and dimensions, then you can decide what is the maximum tolerance you can allow. So here, for example, this is a bilateral tolerance. It's the case where variation is permitted in both positive and negative directions from the nominal dimension. And a bilateral tolerance can be, if you want, balanced or unbalanced. But when we say balanced, this means that I can go in the positive direction by an amount equal to the one in negative one, while I can have unbalanced tolerance on the other hand. So for example, I can say I want maximum a diameter of 2.51. Okay, so in this case, my tolerance in the positive side is higher than my tolerance in the negative side. Okay. Now, another type of tolerance is unilateral tolerance. So sometimes you just permit tolerance in one side, positive or negative, but not in both. Okay. So here, for example, you can allow a higher diameter, but not a smaller one. So it depends on your application. Okay. So here, for example, I can allow for maximum 2.51, but I cannot allow smaller than 2.5 centimeter, for example. Now, what is the limit dimensions? Of course, they are the minimum and maximum dimensions allowed. And once you know the tolerance, you can determine the minimum and maximum dimensions that are allowed. Now, the measurement is the procedure in which an unknown quantity is compared to a known standard one using an accepted and consistent system of units. Okay, as we have seen before. So measurement provides a numerical value of the quantity of interest within certain limits of accuracy and precision, of course. Now, what is the difference between accuracy and precision? In general, in any measurement, I need both. I need accuracy and precision. But what is the difference? Accuracy is the degree to which a measured value agrees with the true value of the quantity of interest. And this is the case when a measurement procedure is accurate when it avoids systematic errors in the positive or negative side. This means that, for example, if you are measuring a mass, okay, you know that any equipment need to be tuned before using it. So, like if you are familiar maybe with the equipment that measures the mass, so for your balance, You tune it on 0 before measuring your mass. Okay, because if you don't tune it, it might give you a wrong result. It can give you this result in a repeated way. So even if you try to measure again, you will obtain a wrong result again. So this is a high precision but not accurate result. Okay, so accuracy means that your measurement is close to the actual measurement, while precision means that this equipment is able of giving me the same a close measurement if I repeat the experiment several times. So precision is the degree of repeatability in the measurement process. Okay, so good precision means that random errors in the measurement are minimized, but to ensure accuracy, you should make sure that your equipment is tuned well. And here you can see an example of accuracy versus precision. So in the first figure, your purpose is to reach the center of this when you do your shots. Okay, so here all your points are at close to the center, so it's a highly accurate thing, and all points are close to each other, so it's also of high precision. On the other hand, in the second example, all your points are far from the center, which is so this is a low accuracy result. While you have high precision because all your shots will be close to each other. Okay. Now, for a third case, in the third case here, you have high accuracy because your points are close to the center, but it's low precision because you do not have repeatability in the location. So the locations are not very close to one point. Okay. And finally, the final example is low accuracy and low precision because all your points are far from the center and they are randomly dispersed on the map. Okay. Now, what are the conventional measuring instruments and gauges? We have several types. We have the precision gauge blocks, which are measuring instruments. We have the measuring instruments for linear dimensions. We have comparative instruments, fixed gauges, and angular measurements. We will see in details what does this mean. So first, the precision gauge blocks consist of standards against which other dimensional measuring instruments and gauges are compared. Usually they are of square or rectangular form, and their surfaces are finished to be dimensionally accurate and parallel to plus or minus several millionths of an inch. So here, the manufacturing of these precision blocks is very complex and accurate. And higher is the precision of surfaces and the finishing of surface, higher will be the price of your gauge blocks. The precision gauge blocks are available in certain standard sizes or in sets, the later containing a variety of different sized blocks. So let us see them here in a figure. And in the YouTube links, you will find a video showing you how to use these blocks. So here, as you can see, you have a set of different dimensions. So for example, here, you can have a notation on it. And this is, let's say, 5 centimeter. This is, let's say, 0.001, for example. Okay, so you can construct any length starting from these gauges. And since they have very flat surfaces, due to the very high finishing of these surfaces, they will attract each other. So if you put one on the other, they will be attracted. Okay. And this allows you to form any length you want starting from these blocks. Now, what about measurement of linear dimensions? Measuring instruments are divided into two types: graduated measuring devices, including a set of marking on a linear or angular scale, to which the object's feature of interest can be compared for measurement. So here, the first type is graduated. Okay, one of the simple device is the rule. Okay, for the rule, you have a rule with graduation, and you can measure the length of any side you want. Okay, you have also for angles. This, you are familiar, of course, with this in geometry. So you have this with angles, with angle graduation. Okay. Now you have other measurement equipment that are non-graduated measuring device, and they have no scale and are just used to compare dimensions or to transfer a dimension for measurement by a graduated device. You might tell me why I don't directly measure with a graduated device. We will see together why. Sometimes it is more accurate to use the non-graduated measuring devices. For example, here, I will show you a figure. Now, this is an example of external micrometer. In this case, what you can do, it's called external because it's used to measure external sizes. So if I have a ball, let's say, I put the ball in between the two sides, and I can measure the corresponding lengths. We will learn together how to read these measurements next time. Okay, and you have other tools for internal measurement. We'll see together. This is the vernier caliper. The vernier caliper is suitable for measuring external and internal measurements, because look, if you have a ball, for example, you can put it like this and you can measure its diameter. Also, if you have a hole, what you do is, so let's say you have a big hole, you put first this inside the hole, and then you can by pushing this outside, okay, you can measure the size of the internal hole. Okay. And look, you have this one here is for external measurements, and the one here is for internal measurements. Okay, so you should put it, you use different sides for, this side is used for external measurements, and this side here is used for internal measurements. Now, this is an example of non-graduated tools. Okay, so for example, if you don't have an advanced micrometer in your lab, which will directly give you the value, you can have these calipers, which are on a cost, their cost is lower, but they're also helpful because if you can put, for example, a ball in between, you can accurately fix the ball between the two sides and measure the diameter just you transfer the length. So you take this length and you transfer it to a rule, then you can read the accurate measurement. Now, mechanical gauges as dial indicators. Mechanical gauges are designed to mechanically magnify the deviation to permit observation. Most common instruments in this category is the dial indicator, which will convert and amplify the linear motion of a contact pointer into rotation of a dial. Okay, and the dial will be graduated in small units from 0.01 millimeter or 0.001 inch. And the application of these mechanical gauges, we have a lot of applications that they are used to measure straightness of surfaces, flatness, parallelism, squareness, roundness, and runout. So for example, here we can see how this is a dial indicator. So you can see how it's very clear. The graduation is very clear on it. So it's used to magnify small deviations, so we can read easily on it. This is a small example. This is a setup where, for example, we can test the roundness of this cylinder, because you know that to be perfectly round, I should have the same diameter across at any cross-sectional area. So what I can do, this contact point will move over the cylinder, okay, and any deviation from the radius will lead to deviation of the dial, okay, and in this case I can measure what is the maximum deviation over my cylinder to see if it's close to a purely cylindrical shape or not. Okay. Now, of course, with the advancement of technology, electronic gauges are becoming more and more important. Okay, and in general, we are still using the mechanical devices because the cost of electronic gauges is relatively high. So a family of measuring and gauging instruments based on transducer capable of converting a linear displacement into an electrical signal is electronic gauges. Electrical signal is amplified and transformed into suitable data formats such as digital readout. Applications of electronic gauges have grown due to the development in technology and advances in microprocessor technology, and are gradually replacing many of the conventional devices. Just the limit that you know that they are used in very advanced labs, okay, because their cost is high. So these are examples of electronic gauges. So instead of reading ourselves the measurements, they will directly give the digital result. Now, other types of measuring devices are go and no-go gauges. Okay, they are named in this way because one gauge limit will allow the part to be inserted, while the other limit does not. Okay, now we say that the go limit is used to check the dimension at its maximum material condition. Why we say maximum material condition? Because we will see together that the go limit will allow to measure the minimum size for internal feature, such as a hole, and the maximum size for an external feature, such as an outside diameter. While the no-go limit is the opposite. It's used to inspect the minimum material condition of the dimension in question. Let us explain this. This is a go-no-go gauge. Okay, as you can see here, if I insert a ball inside the go-no-go gauge, okay, the idea here is that I have here the difference between the go and no-go is very, very small. Yani, 0.00 something. Okay, so let's say, for example, I write here, this snap gauge will give me a size of 6 centimeters, for example. This means that if I have a ball and I introducing inside, it will pass over the go gauge button, but it will not pass over the no gauge button. Then I can say that the actual measurement of the diameter is 6 centimeters. Okay. Now, why we say that the go gauge measures the maximum material condition? Because here you can say that the maximum size of diameter, okay, will correspond to the difference in distance between these two buttons. So this is the maximum material condition. While for the no-go gauge, because it's not passing, the ball is not passing through it, it's measuring the minimal material condition. Okay, and if I'm having a hole, okay, then the gauge, the go gauge will measure the minimum value of the hole. Okay, this is why the minimum value of the hole will corresponding to the maximum material condition, because lower is the size of the hole, higher will be the amount of material. This is why we say that the go gauge measures the maximum material condition, which correspond to the minimal internal side and the maximum external side. Okay. And for the no gauge, it's the opposite. It's measuring the minimum material condition.
Doctor?
Yes.
Can you repeat what you said? You said something that you give the example of 6 centimeters, and you said that this ball, it passed the go gauge, but it didn't pass the no-go gauge.
Okay. Okay. So in general, you have several snap gauge, and each snap gauge will give you a size. And for example, if you have a ball and you want to know its diameter, you should pass it through a series of snap gauge until fitting one of them. What is the idea? The idea is, for example, if the ball is 6 centimeters, okay? If you try to pass it through another snap gauge, okay, of 7 centimeters, it will go through the two buttons, okay?
Okay.
While if you put it, if the snap gauge you are using is actually the size of it, what will happen is that the ball will just pass by the go gauge and will not pass through the no-go gauge. And you have triggered really what is its size. Okay?
Okay.
So here, if you have a ball of 5 centimeters and you test it, it will pass.
It will pass.
It will pass, so it's not its size. Okay? So,
okay.
Of course, maybe it's not very practical, but what in general, when we use this, we use standard sizes. Okay? Let's say in a certain application, you have standard sizes, then you can test what is the actual size of the equipment you have.
Okay, so the no-go gauge, it will test the maximum
that can enter. It will not allow to
enter.
pass. It cannot pass. كأنه your ball is triggered here. It cannot, it just pass by one of the gauges and it will not pass by the no-go gauge. So it's just its size, the accurate size. Okay.
Okay.
You have two possibilities. If the size is smaller than 6 centimeter, it will pass by both. If the
Yes.
size is higher than 6 centimeter, it will not pass by the go gauge, and of course, it will not pass by the no-go gauge. Okay.
Okay.
Now, if it is the accurate size, it will pass by the go gauge, but it will not pass by the no-go gauge, because the difference between these two is very, very small. This is why you say that I can catch the true dimension by this way.
Okay.
Without any tolerance?
Of course. What is the tolerance here? The tolerance is the difference between the go and no
Between
go.
the go and no go. Oh,
Yes, the
okay.
difference, but the difference is really small. Of course, so depending on the accuracy you want, it depends on the snap gauge you are using. So lower is the difference between the go and no go, higher will be the accuracy. Okay. So let us continue.
Doctor, you said something about a hole.
Yes, if I have a hole and I am measuring it using a snap gauge, okay, then the go gauge, what will happen is that the go gauge will pass through the hole, but the no gauge will not pass, okay? This is why we say in this case that the go gauge is like measuring the minimum diameter of the hole, okay, which correspond to the maximum material condition. So here you can see it here. This is a plug gauge, okay? Let's say you have a hole and you want to test what is the size of the hole. So what you will do, you will try to pass your gauge through the hole, okay? Now, the go plug should be just little smaller than the hole, or to just go through it, okay? And the no gauge will not pass through the hole. This means that the go plug measures the minimum diameter of the hole, okay, which correspond to the maximum material condition. Because the lower is the diameter, the hole, the higher is the material. Okay. And always here, as they said, the difference in diameters of go and no-go plugs is exaggerated. In the real case, the difference is really very small to give you a good accuracy in measurement. Now, this is a type of another type of measurement equipment, but it's used for angles. I will also tackle this with you in examples in next session. Now, what about surfaces? The surface characteristics are very important, okay? In general, the nominal surface is defined as the designer's intended surface contour of part, defined by lines in the engineering drawing. Nominal surfaces appear as absolutely straight lines, ideal circles, round holes, and you know that in reality it's not the case, okay? So actual surface are determined by the manufacturing processes used to make them. More accurate are the manufacturing processes, closer will be the quality of the actual surface compared to the nominal one. Now we have a variety of processes resulting in wide variation in surface characteristics. So for example, here you can see in this figure, you have different surfaces produced by different manufacturing processes. We will go in future chapters in detail over what is horizontal milling, what is vertical milling, what is turning processes. So just here you can see that depending on the process I use, the quality of the surface will vary. Now, how to assess the quality of the surface? We will see that we can define the roughness of a surface as a quality. Surface manufacturing is very important due to different reasons. First, for aesthetic reasons. Second, for safety effects, because you know that, for example, in a thermal, if you are using combustion engines equipment, the piston should go in translation in a cylinder. So the surface of the cylinder should be perfectly smooth as much as possible for safety purposes, to not have corrosion of the piston surface and of the cylinder surface. Friction and wear also depend on the surface characteristics. We have seen that the tools used in manufacturing should be resistant to friction and wear to operate for